So because limited time, so I think what I'm going to do is to really maybe go through in more detail of one toy model, a very specific example to show the general ideas, at least me and my colleagues are trying to do to model those phenomena. Then I will give some reference list to some other work and some other introductory chapters or papers for those people who are interested, just want to start to explore this field. We found it's quite exciting. Like Thomas and Carl has said, we believe there are a lot of interesting potential, and I'm sure you'll hear a lot from the following talks too. So why quantum models? I think Thomas and Carl has mentioned many reasons, and here I would like to highlight three. So quantum theory is really a general axiomatic theory of probability. So one, as a cognitive scientist, right, the early work when it's under review or when we present our work to our colleagues, one of the typical challenges is that why do we need this, right? Why do we need something from physics? But if we're looking at the current model we're doing, actually, they're all coming from physics as well. So quantum, besides the mechanics part, the mathematics and probability theory is really general for us to use as well. So human judgment and decision, they are probabilistic, and that's the big focus of our current work. And this probability do not obey, based on our empirical work, do not obey the classical Kolmogorov axioms. So what we're trying to do is not only top-down saying, hey, this is cool theory, we would like to apply it, but also because the data does cry for some new explanation, like Thomas has already argued many times. So quantum theory provides a viable alternative. Is it always necessary? Probably not. But we have some ways to test, right? In what kind of experiments, what kind of situation, what kind of context, the quantum theory, quantum-based models provides better explanation than the classical ones. So, and the second is maybe one of the particular most important property of the conception of the computational and mathematical tools provided by the quantum theory is the now commutativity of the measurements really provides a very nice conception and tool for us to formalize the measurement issues in psychology, in cog science, social science in general as well. And that's what I'm going to focus on today. So the principle of complementarity was borrowed from Neil Boyce, from William James, which is one of the founders, one of the most important founders of psychology, right? So the third is for those of us who do modeling in cognitive science or do the computational modeling in cognitive science, so the vector space presentation of the probability actually is very much agrees with what we have been doing in the field already. So it's not that odd or strange. It's really just maybe one or few steps forward. So a lot of work, like for example, the memory models really was based on those multi-dimensional space models. So now when we stand into the quantum structure, the vector space, Hilbert space, it does provide a lot of advantage. And some of our work have like empirically tested this and showed the strength of the quantum ideas. So that's not all the reasons, but the three reasons I would like to highlight. And let me start with a very small and simple toy model. So this is not a real model, it's just a toy model. And typically we have high dimensional space models, but here I only show you two-dimensional just to illustrate the idea. So here is the question. Actually asked many times, and it's quite a well-studied question from Gallup poll, right? One of the largest public opinion research organization. So this question has a lot of relevance in the current world, especially in the United States. So the question asks us, do whites dislike blacks? So it's a hostility from the white people towards black people. So, okay, and what do we do in our, maybe I should get out of the presentation mode so I can use my mouse to show you. Okay, maybe this is better. Let me think this is better. Hold on. Is this all right? Everyone can see? Okay. So in this case, let me show the toy model. Again, it's not two-dimensional, just for illustration, right? It's oversimplified with the two-dimensional. So what we will do, represent is using a two-dimensional with the x-axis shows it's the subspace, it's ray shows the yes, whites dislike black, if you think it's yes. And the y-axis, this vector is the subspace to evaluate no. So because when you answer this question in this very simple example, the question is yes, no. Of course, you can have 1 to 100 point scale, other scales, and we have models for those as well in our publications. But here, let me just using the simplest example. Do whites dislike blacks? Yes, no. You have two answers. So we're using such a model to represent how people would answer this kind of question with yes, no question, yes, no options. Then the probability to say yes in this particular example, given your initial state is here in this bright blue ray here, right? Again, it's simplified, it's one-dimensional, right, in this case. So in this case, what we would compute the probability for saying yes when your initial state is here. You can be anywhere, but in this particular example, I just made it here, is to project this initial vector, initial state to this yes subspace. Again, oversimplified, just one-dimensional ray here. And then for the projection, right, that's a projection. So it's just like a shadow. It's a projection like the regression lines too. And what you do in quantum probability model, you will take the squared length of this projection, and that's the probability. So in this particular simple example, is take the square of this projection will be 0.4. So in this one particular example, the probability to say yes, given your initial state is here, is 0.4 to this question. So, okay. And then now, if you repeat the question after you're answering yes already, right? But now you ask different ways. You ask, do whites, before is do whites dislike blacks. Now you once again, you ask, do whites dislike blacks? You're already collapsed on this yes ray here. So now it's this collapsing to this subspace in this particular ray made your your state is updated to the subspace. So now your initial state is not here anymore. Now your state has been updated to the subspace of yes, you truly think white dislike blacks. So the probability of yes given, you're already, right, your state is yes now, is 1 now, because you will just be sure to say now you're certain about this answer you have. So this is repeat or collapse effect in quantum theory. So now, however, if you ask a different way, right, from a different perspective, you change the perspective. Now you're not asking do whites dislike like blacks, but now you're asking the other way around. It's do blacks dislike whites? Now it's now I have to think, change my perspective now from the blacks. Now you're not in the shoes of the whites anymore. You're in the shoes of blacks. So how do we represent that in our quantum cognition model? We rotate And this is something more complex, but I can explain later. But what you can do is rotate the evaluation space to this red cross here. This is in this case, again, oversimplified two-dimensional space here. Now, this line, this vector is the subspace to say, yes, blacks dislike white. And the orthogonal vector here is the subspace to evaluate, no, black do not dislike whites if they are incompatible, which Thomas mentioned, which actually is one of the most important concepts we believe in applying quantum theory to cognition. So in this case, you have actually in the modeling, you do have a parameter fitting or theory-based reason to formalize this process to rotate the base for evaluation. So which is super interesting to us and was explained in multiple papers we have, because the relationship, how you rotate your perspectives is of a lot of psychological interesting to us, right? Because how you think as whites, how you think as blacks, this relationship between those evaluation bases should vary by people, by context, by many things. And it can be compatible or become incompatible and vice versa. So there are a way to parameterize this process, which is very interesting psychology process. Okay, now the other scenario is, now what if you ask this two questions back to back? You first ask, do whites dislike blacks? So what, WB order. And then now you ask, do blacks dislike whites? The BW, right? So if you ask those two questions back to back, which is exactly the public opinion research firms and companies do, right? They randomize the order of those kind of questions, because they know there will be an order effect somehow between, if you ask WB first or ask BW first. But how do we model this? So in this model, then what this does is the sequential projection. So the probability of yes to WB question, and then, so it's not joint probability, but it's something called a sequential probability, as we say, because you can't think about both questions at the same time. So sometimes when we face this kind of question, right, it's less familiar, maybe we're less feeling certain about those questions, like you have to evaluate them sequentially. So it's yes to WB and then yes to BW given your initial states, again is here, will be something like that. You project your state to the yes to W first, and then project to the second question. So again, you take the squared length of this projection. In this particular example, again, it's just an example here. Then the probability is 0.36 for this particular case. If you have initial state here and you have some relationship between the two evaluation space like that, right? Again, just example, okay? So from this very simple toy example, we can see how we can predict this order effects. Right, so now this is just what we showed. Now, if you ask the other way around, it's the same person, have initial state here, and has the same relationship between the two evaluation space, but the only difference in these two figures, is the way, the order you answer two questions. So in the left panel is WB and then BW, and in the right panel is BW and WB. So in this particular case, then you would project from your initial state to the BW and then to WB. Now you can see nothing of this person's mind has changed, but only the way the measurement, the order or sequence of the judgment has changed will create different answer to the person's joint probability, but not joint. It's really sequential. That's how we explain it. It's a sequential. You have to project sequentially. So in this case, for example, in this example, the probability of yes to both questions is much less than the other order. It's not 0.36. It's the squared length of this projection now. Now it's 0.12. So again, this is just the illustration. And now I'm going to show you, I believe I'm going to show you some true studies we have done. So the attitude question order effects, A question first and then B, or B question and then A, is really well studied in public opinion research. For example, David Moore in 2002 has published a review paper in Public Opinion Quarterly, and David Moore was the vice president of Gallup poll for a long time. So people really realize this problem, right? And that's why in our experiments, right, in our psychology experiments, in public opinion research, in any kind of social behavior experiments, we typically randomize trials, randomize question order, or randomize rating scales to hopefully maybe cancel out the noise, right? Take the average. And that's what public opinion research has been doing is they found that they typically post hoc find the question order effects and then they describe the phenomena, but there is not a very good theory about this. So we published a couple of papers on those phenomena with a prior predictions and with some very strict test on the model. So this answers some of the questions from the audience earlier to Thomas, is that what kind of test we have done. So I think people have done a lot of tests, and here is one example. So order effects are pervasive in psychology, as just said, not only just in public opinion research, but also like in research on inference for probability judgment, like for conjunction disjunction phenomena, there is order effects as well. And actually order effects is also in like information science, in computer science, for example, in document relevance judgment, right? Judgment something is important or should be ranked high or not. When you do a Google search, is this document relevant or not? Is it should be ranked high or not, such and such. So typically, those at least in psychology and in most social behavioral science, this order sequential effects in measurement has been veiled as noise, right? But we believe there are evidence for the essential, very essential constructive nature of human cognitive measurements, in particular the incompatible measurements. So when you, in a way, like when you cannot think about the two measurements at the same time, you have to answer them in order. So what this really means in psychology language is that attitudes are not entities simply retrieved from memory and recorded. So instead they are constructed. And this is actually a long time, time tested and honored social psychology theory in the constructivism on attitudes. So the thoughts constructed from the first question can change the context for the person to use to evaluate the second question. Right? Quantum theory provides an elegant way to formalize this. So it's not really something so bizarre or so psychological new. It really provides new tools and very specific conceptual tools and the mathematical and computation tools for us to formalize those kind of intuitive, maybe more vague verbal theory. And also, this is what I would like to highlight. The exactly same model. So the same model, just like I showed, very simple, very same model. But of course, you can be high dimensional, as I mentioned, can explain a myriad of many other puzzling phenomena. And I will provide a list at the end of my talk. So to us, that's the strength of a theory, of a model, right? So we do not want to post hocly come up with all kinds of different models and explanations for things we suddenly found we need to explain. But instead, we can have one single theoretical account for many different phenomena. Actually, some of them, we never connect them before. So here is really the empirical data. Let me again give you the example using this particular question as example. So this question about hostility between whites and black people, right? In the real actual data from Gallup, for example, in the particular one data set, they have national representative sample and randomly selected 500 of them to answer BW order. They ask about the hostility about black towards white first, and then hostility from the white towards the black. And then the other half, right, the randomly select the other half, answer in the other order. So again, yes, no question. So the only difference between those two conditions is the order, black or white or black. So this is the data. So you can have, for this first pair of question, you can have a 2x2 matrix for the probability of the yes, no combinations. So in the white W, actually white W is this one, white W, white first and W. So data is here. So if you say W, say yes to the W or no to the W question. Or yes to the black question and no to the black question. So you have yes, no, yes, no, right? So those are the combinations, what we typically call joint probability. But again, we believe it's a sequential. It's not really joint produced. So this is the data. The sum up should be 1, right? About 1. But maybe we exclude some data, so it's not exact, but it's roughly about 1. So you can produce the same 2x2 matrix for the other order. Now let's take a look at just one combination of the answer. When people answer yes to the black hostility and no to the white hostility question. So in the W, B order, so if you ask the white people first, actually about 16% of people in the population would say, yeah, would give this answer, no white, yes to the black. And that number significantly reduced when you ask the black first, ask from the black perspective first. So actually this is a big 10% reduction in this case. So this is quite significant, right? So, and it's very easy to test. For example, in this particular case, the chi-square test is significant for this kind of order effects, right? So what's interesting is that how to test this. So so we derived a very, very strict prediction based on our model. So if assuming one question followed immediately by another question, like the white hostility followed the black hostility question without any other new information in between, what this means is that you just collapse to one substate to the other, right? Without collapsing to some, some information in between. Then what we will derive from the simple model I presented using this very simple toy example, you have to derive such a relationship with what we call QQ equality. So basically, the probability of you say yes to A and then no to B would be a sequence of this, right? But then if in the other order, you say no to B first, and then yes to A, right? The only difference is the order. In quantum probability, it would be collapse A's. So in the former case, it's A's collapse on the A evaluation and then collapse on the B evaluation. But in the second case, in second order, it's collapse on the B first and A. So you could derive something what we call QQ equality to give it a name. It's called quantum quotient equality. But anyway, it's a very interesting equality. We provide the proof in our publications I cited earlier. You can read those if you're interested. But this is very bizarre from psychology perspective. We would never have this kind of hypothesis if not because the model we had, right? So basically what this says is that it's kind of this the probability of you say in the AB order, the probability you say yes to A and no to B, plus the probability you say no to A question and yes to B question would be equal to what you get in terms of yes, no, no, yes combination in the other order. So this is quite bizarre if we take a moment looking at this, right? So basically, it means if you have change, for example, if you have change in one of the combination, yes to A, no to B, yes to A, B, no to B, in one of the combination, you have to offset that change in other combination, which is very bizarre psychologically. I would never expected this psychologically. But this is derived from the mathematical model we have on this vector space model we presented. So okay, this is very easy to test because, so this goes back to one of the questions from the audience. It's a very excellent question. How do we test those? There are many ways we test the model. So typically in cognitive science, we do parameter fitting. We fit the parameter and try the different ways to compare models, including the complexity, goodness of fit, and so on. But in this particular case, we do not need to fit the model at all because it's parameter free, because all those numbers are observables from the data. We don't have to estimate the model. We don't need to fit the parameters. Those are just a very simple test, but very hard and strict test on the model too, because you can easily get those and you have them sum up to be 0 with this QQ equality here and here. So that's what we did. So what we did is that so this was what we published in the PNAS in 2014, is that after we derived this equality, I said, okay, this is really easy to test, right? And very exciting, but also nervous for us to test because it's so easy to be falsified. So what we did is that we wanted to use a Gallup poll to gather whatever available from Gallup poll in the past 10 years. And we worked with Gallup poll for whatever they have still in their finding and documents. All the cases, they had some AB versus BA type of order, no matter what they found. But just if they ever did split the sample into AB and BA. So we just wanted to find, and we were able to secure 32 large national surveys. So it's all national representative sample in the United States and over the last 10 years. So the first step is to test the QQ equality, right? So what do we test, for example, in this particular example? Indeed, it's offset almost equal, right? The change in one combination should be the same as the other. So the QQ equality is easy to test for each particular survey, each particular data. But what we did is that we gathered 32 samples, 32 big studies, right? And then tested on all the 72 studies. Actually, also include some of our own Lambo experiments too. So this is the results of the 72 national surveys over a decade. So the mean sample of people in each survey is more than 1,600. So it's quite a large sample for each survey. And first we test the order effects. Why we need to first test the order effects? Because if we look at here, if there is no order effects, then QQ equality should hold for trivial reasons, because sure, it should be 0. It's only interesting when you have this change because of order, and then this equality holds. So first step is test whether there is a order effects. And indeed, there is a significant order effects across all the 72 studies. And then we test the QQ equality across the 72 studies. And yes, again, the QQ equality holds. So let's generally support our model. And in the supplemental information, we have tested some other maybe arguments, because our colleagues, right, like in cognitive science, have all kinds of very creative and brilliant ideas about what if, this kind of model, that kind of model, which is fantastic. And we know many groups are doing model comparison with our model as well, with this kind of, with our old data here. So one of the questions coming up after we publish the paper is from people in the quantum group, actually, quantum cognition group, is asked, what if it's ABA, right? What if it's not the ABBA? But what if you ask the A question and B question, right? You change, update the states. Now you ask the A again, because the B should interfere what you believed about A, make A uncertain again. It's just like the Heisenberg uncertainty principle, right? You become uncertain about A again. So great. So it's like in this example, we have hostility question again. Maybe we ask, do whites dislike blacks? Do blacks dislike whites? And now, given that you have just thought about how and whether or not black people dislike whites, now what do you think at this moment? Do whites dislike blacks, right? So really from the quantum view, constructivism view, with if you feel somehow ambiguous about those attitudes, right? Ask the B question here. So after feeling certain, collapsing and measuring the black, from the black's perspective, you kind of being disturbed again. You feel a little bit ambiguous, uncertain about whites again, although you felt differently maybe before. So it's kind of this B question interferes with the A question. So here we use A prime to indicate the second measurement on A. So let me again going back to the toy example to illustrate the idea. So for example, before you answer yes to whites, the white question, right? That's your state, your initial state, your collapse. That's what we showed before. You have this 0.4 probability to say yes, whites dislike blacks. And now after yes to whites, right? You collapsed on this evaluation space already. So the probability become 1 because now you're certain. After you said, yeah, that's what I think. Now you're certain about your attitudes. And now after yes to the black though, right? If you have yes, you collapse on the black, which is the red vector here. Now after you said yes to black, your state is here. Now you become uncertain. So here is like certain. You're certain about the second, the middle panel shows you're certain about your attitudes for the A question, the white question. But now, after you're answering the B question, the black question, right? Black hostility question, you become uncertain because you're not in this subspace anymore. You're not in this evaluation space of the white hostility anymore. Now you're in this subspace of the red, of this black, this red vector, this black evaluation here. So if in this case, your potential to say yes, right, to the white question, to answer the A prime question. So this is like A, this is answering A after A, kind of AA, and this is like answering A after B, right, BA. So in this case, it's 0.9 probability. In this case, it's 0.1. Did you see the difference? So this is like you're certain 100% you will say yes, but in here 90%, right? 0.9 probability to say yes. So this is like what we believe is formalize this idea about kind of Heisenberg's uncertainty principle. So inserting the BW question in between the WB questions reintroduce the uncertainty about the WB. So the psychology ideas here is that you really cannot think about the two questions at the same time, right? Because it's not something you think about every day, but maybe you will become like, the two questions maybe become compatible now, with the news media and this big social problem right now in the United States. But if they are incompatible, you will reintroduce the uncertainty into the problem right here. So that's a toy example. So now the prediction, this is what is interesting to us, because this new prediction we derive from this model again. Now we generate a new prediction for this uncertainty effects. So after answer yes to black, right? That's what we share. So you reintroduce this, but you can see this uncertainty you reintroduce vary because the relationship of the two evaluation space. So when this evaluation space for the black is right, in a way, move away, your last, it's like the BW, the yes to the B question actually is rotated away from this subspace, the green subspace. You can see you introduce more and more uncertainty, right? In this first panel is 0.9. In the second example, you move this evaluation subspace farther away from the white evaluation subspace is 0.65, and in the third you move farther away is 0.36. So it's like a interesting phenomenon, interesting prediction we haven't seen in the literature at all, right? It's like increasing rotation of the BW actually should increase the interference effects. So in other words, decreasing the correlation between the answers to questions increase interference, right? So like if this red vector is closer with this green vector here, so like yes to the yes, black people dislike white, yes, white people dislike blacks. If they're closer with each other, it's kind of like the angle, actually it's cosine angle of this angle. When it's kind of like this similarity measure, I think this interesting comments coming from this question from the audience as well. It's like from the kind of relationship between these two vectors, evaluation subspace, when they become closer. So it's like a correlation between answer to questions. If this is increase, going this way is decrease. If it's decrease, it's less and less correlated. If decrease correlation between answers, should increase the interference, should increase the difference between the A prime questions, right? So basically that's the prediction. It's like if the A-B correlation, A-B answers, they're more correlated, the interference effects should be less. But otherwise, if they're less correlate, decrease the correlation, they should increase the interference. It means the A and A prime correlation should increase. The difference should increase. Sorry, the difference should increase. So that's what we did in this experiment. We call ABA experiment. It's published in PLOS ONE. We had 325 people, and they are doing this ABA about 12 pairs of issues. So some examples, the 12 issues here, like the judgment about whether you approve or disapprove the presidents in the United States, and are you happy with the country, right? Which is a question constantly asked in the Pew Research Center, by the Pew Research Center. And affirmative action for women or the affirmative action for the racial minorities. And are you happy with your life Are you happy with your relationship? Right? That's again another classical, very famous question in social psychology, in psychology. You know, abortion. Are you supporting abortion with certain reasons? You know, or without certain reasons? So those are very realistic questions, constantly being actually examined in the public opinion research. So all the 12 issues has been found to produce order effects. So that's why we knew there is a, so that's why we know A and B, the measure, are incompatible, right? Because when it's become incompatible, then it's become relevant for us to apply the quantum theory. So each question rated on a 0 to 100. So it's not a yes, no question, it's a 0 to 100 scale. So it's a more refined rating scale model we published here. So but now going back to our hypothesis that we want to test, like this hypothesis I mentioned, is interesting finding derived from our model, and whether it's true, we need to test it. So what we test it is using the data, right? First, we can plot, actually in this particular plot, the x-axis indicates the root mean squares deviation on 0 to 100 scale across all the 12 pairs of questions. So really, we suggest A to A prime. Indeed, right? It's not homogeneous. Some people do not show any. And that's what we found actually very interesting over years in our research is that not everybody is quantum-like, right? Not every situation. It really depends on people, context, and the variability cross context and cross people are very interesting. So if you plot this across, so this y-axis is a proportion of people, right? From the 300 plus people we have, and this is the root mean square deviation. Is a deviation on the scale across all the 12 pair of questions. So you can see some people show a great change. Actually, 25% produce a change exceeding 15 standard deviation. So some people show great deviation from A to A prime, from A prime to A. But there are people who didn't show much. But still, in generally, a lot of people show this deviation, this change from A to A prime. So now, this correlation is really interesting for us to test. Is
working laboratory psychology and cognition on the Center of National Research, Scientific Research in the US.
Okay. So is a question? Sorry. Okay. So each issue produced a correlation between a pair of answers. So like the key test we have is here, right? So it's very easy to test. So we just compute the correlation Pearson's R between A, B for each person, right? For of course all the people, and then R square between A and A prime. Actually, it's A and A prime. So like we predicted here, we should predict that we should expect that decreasing the correlation between A, B should increase the AB difference, AA difference, AA prime difference, right? Should increase this interference. So that's what exactly we found. And the correlation between the 12 pairs is quite significant. It's 0.86. So you can see for, yeah, I think maybe I'm running out of time. But anyway, so so there are a lot of, so the same model, exactly the same type model has been used to explain conjunction, disjunction probing judgment errors. And Busmail, Pathil, Fakal, and Trubla, they have a very nice psych review paper in 2011, reviews this phenomena. I know I will skip that. And also, kind of the psychology version of the double slit experiment. This is a paper Ramos sent in the chat box here on Zoom. So in this case, that actually we fitted a kind of very parameterized the model and fitted the model and compare our model with some other model to test the interference of you're doing a categorization and how that categorization can interfere your decision later. So we have to use some concept of entanglement, and it's a dynamic model. We're competing the model with maybe the most state-of-the-art model in the field right now with the diffusion decision model in the field. So I'll skip those. And we also had, of course, like we realized a criticism, right, from people who are suspicious about this approach, which is totally justified, is that, hey, quantum sounds very complex, right? In the quantum science, it's all about we need a simpler model for better fit. So in the past work, in a lot of work we have done is to do very careful, make sure the number of parameters kept the same between the competing models. But in more recent work, including this paper as well, but in particular in this decision paper, we did a Bayesian factor comparison to compare. So not only this consider the number of parameters, but also consider the kind of the complexity of the mathematical structure of the model as well, comparing the classical model versus our quantum version of the model. So this is another phenomenon. Yes.
Dr. Wang, we only have, we are almost done with your presentation.
Okay, perfect. I'm finishing up.
Yeah.
Thank you. So that's exactly where I'm going to end. So there are many more applications, and I'll be happy to send this over chat or in other, and please feel free to email me if you want those other reference. And there are more applications from the group of us who doing the same type of model applying to many different phenomena. So the basic conclusion here is that why we like this approach is that quantum theory provides an alternative framework for developing probabilistic and dynamic models for decision making and other cognitive phenomena like memory models too. Provides a coherent account for a lot of puzzling violation of classical probability found in quite a different type of judgment and decision making studies and other cognitive studies. It forms a new foundation for understanding widely different phenomena. So we thought it's quite elegant and quite coherent, and really using one single theoretical account for many different phenomena that we haven't put together before. And I know Dr. Castillo told me that there are students in Cognition in the audience. So if you're interested in reading some introductory paper, and here are a few short introductory paper, and there are some special issues too, and many others as well. And of course, there's a book by Busmayer and Bruza, and which went through a lot of details of the early model. So this has been published in 2012. So we have a lot of new progress, but this does provide a lot of kind of tutorial type of procedures for how to do this kind of modeling if you're interested. So yes, thank you. That's all I have.